Hello, welcome to this wee video on the Riemann hypothesis. That's a fabulous tricky problem in mathematics. This is really going to focus on the zeta zeros and the meaning of that tricky little half. RH has its origin in an incidental comment made by Bernard Riemann in his 1859 paper entitled On the Number of Primes Less Than a Given Magnitude. He was 33 at the time. It was the only paper he did in number theory. He was pretty busy doing stuff in physics. What does pi x look like? Well, let's have a look. This is a plot of it. It's the staircase function. It's an empirical function, meaning that certainly before this paper, the only way to work out where the steps were was to calculate where the primes were. Various people who did this over time, I think even in Euler's day, which goes way back. 100,000, the first 100,000 primes were known, and then Gauss sort of carried that on to about 3 million. He'd do 1,000 every day. Such he was. So here's a couple of asymptotes to the function. These are sort of classical asymptotes. And it looks as though the staircase function pi x is bounded by these asymptotes. But that's only 1,000, so don't be fooled. It has in fact been proven that they are genuine asymptotes and that the pi function does approach them. That was succeeded by a couple of guys some years after the 1859 paper. But also the English mathematician Littlewood proved that pi x does eventually cross logarithmic integral of x live x, but he doesn't know exactly where it is. It happens. I have a feeling it might be at the skews number, which is a very, very big number. No way we're going to get there with the computers we've got today. But that's interesting. So really, pi of x weaves around live x. Okay, that is the prime number theorem, which describes asymptotic distribution of prime numbers. There's the two functions. This one, I think, was discovered by Gauss, the x over log x, and the log integral of x. I think it was Dirichlet, I'm not sure. So there's a definition of it. It's there it is. It's an integral from 0 to x, blah, blah, blah. Dummy variable t is a special function, meaning it's not an elementary function. It's not a sine or a cosine or an exponential. Here's a quick sketch of it. The sort of smooth line is live n x, whatever I've put there. And here, this little tiny step thing is the sum of 1 over the reciprocal of the logs, which only goes to show that integration works. The integration is, of course, the sum. The Riemann integration is Lebesgue integration is a little bit different. So that was good. So we've got pi of x here. Now to get to pi of x, Riemann, I think he invented j of x, which is the prime power counting function. So we can see here pi of x goes up 1, as indeed does j of x when x is a prime, 37 for example, whilst j of x goes up a half at a prime squared, which 25 is 5 squared. That's the nature of that beastie function. Again, you would probably have to work all that out by hand if you wanted to do that. Anyway, j of x is always larger than pi of x. So why is he doing this? Well, it's because Riemann found a way to construct j of x from simpler functions, which eventually involved the zeros. So let's have a look. J of x takes on rational numbers, jumping up 1, blah, blah, blah. Jumps up a third when x is a prime cube, and so on. So it's quite well organized. And the way to get from j of x to pi of x, which is the goal, this is Riemann's primary goal is via what's called a Mobius inversion, and the Mobius inversion requires use of the Mobius function. Now this is the same guy, Mobius, who did the Mobius band. He also did a few other things, or a few actually, which is a kind of indicator function, and it works on square-free numbers. A square-free number is a number that does not have any powers of more than one involved in it. So Mobius of 6, which is 2 times 3, would be -1 squared, which is 1, whilst Mobius of 30, which is 2 times 3 times 5, k is 3, so that would make it -1. So there we go. He's building up building blocks there. Mobius inversion. This is the definition of it. It's not an infinite series because when a term falls less than 2, there are no primes, so the series ends. You just need to work out how far you need to go. And all these coefficients and exponents are in fact square-free numbers. Square-free numbers are incidentally quite dense in numbers. The density approaches 6 over pi squared, which is roughly 61%. So 61% of all positive integers are, they're square-free, which I found surprising at the time when I first discovered it. So before we head off into school maths, let's have a quick look at what, this is his paper, this is where he started. 1859, Gauss and Dirichlet were 2 of his supervisors or mentors, and his starting point is the Euler product, which is here, which is this expression here. This is a product, that's 1 over prime to the power of s. Others had used s as a real number, but Riemann was very comfortable with s as a complex number. In fact, it's essential. So this product is in fact equal to this sum, which is actually a Dirichlet series, although it might not have been called that at the time. So this is what he does. He starts there, and then he gets into some really crafty maths. I think that might be a Milan transform, like contour integrals and all sorts of stuff. So he basically extends this function here, which is only valid up to s equal, the real part of s is 1 or greater. He extends it to the entire complex plane using all this crafty maths. In fact, he invented quite a lot of this crafty maths. Such was the guy. That's t squared. He had his own way of expressing things, which is what you might expect. 1859, while back. Things hadn't really become conventional by then. And he carries on. He finds a functional equation that allows you to work out values of zeta in the negative half of the plane based on values in the positive half of the plane. Does a couple of proofs of that and more stuff. And this is really where he ends. This is the main piece, so we'll jump back to that when we get to it. So there we go. That was pi of x comes from j of x. So his goal is to construct another way to construct j of x using analytic functions. J of x is of course a discrete function. It's only goes up in rational amounts. So the zeros of a function. This is school time stuff. We did this. Well, I did this a long time ago. This is real, x is real. It's a sort of basic quadratic. This one's x squared plus c, the blue one. And that's just the modulus of it, because we need to sort of take that on board for the next section. So the zeros, or as we used to call them, roots, actually I think Riemann called them roots as well, are where the function crosses the x-axis, because that's where it goes to 0. And that's very straightforward. So as you change the y-intercept, there's always two zeros, you get to 0, there's still two zeros that are on top of each other. And then you go up there and you go, well, there's no more zeros, no big deal. And quite easy to deal with as a sort of simple function. But something not taught at school, at least not at my school, is the fundamental theorem of algebra. Every non-zero single variable degree n poly with complex coefficients is counted with multiplicity exactly n complex zeros. So all quadratics should have two zeros. You know, a real number is a complex number, it just doesn't have imaginary parts. So we really want two zeros, and yet we just saw that there is only one zero. So now we go off into the complex plane domain. This going that way is the x-axis, going this way is the y-axis. This is the same function. You just replace x with z, and z is a sort of, you know, whatever, x plus iy. Z is x plus iy. So this is where we were before with c somewhere down there. And we can see that there are in fact two zeros. This line here is actually x equals 0. You just have to get used to that. Yeah, because iy is 0. There's no complex part on this line, so it's the real axis. So if we now move towards no, there we go, x is roughly, c is roughly 0, so this is the two zeros are sitting on top of each other. And then when we go to this situation, which was very much this one, where we couldn't find any zeros, what's happened is the zeros are there, they've now gone over into the complex plane domain, and they're there and there, wherever they are. You know, they move out, I think, yeah, further out. It is quite nice. I mean, functions of complex variables are wonderful. If you haven't studied them, recommend it. So there we go. This is when we talk about zeros, we're now talking about this type of zero. So we've illustrated it here with a sort of very simple function, friendly, cuddly quadratic. But what Riemann did was he constructed zeta, and then, the reasons best known to him, he constructed another function that shared the same zeros as the zeta function, and he did that so that he could actually factorize that other function, a bit like factorizing a polynomial, where you multiply out all the various factors of x minus a times x minus b times x minus c, etc., where a, b, and c are in fact the zeros. He took a guess at that because it's not obvious that that was possible. He didn't prove it at the time, but somebody else did later on. Quite a lot of his paper doesn't have proofs, but fortunately other people picked it up and filled in the details. So the Riemann Zeta function is a complex variable, so its input is domain. It's a bit like this. It's the complex plane. It is two-dimensional. The output is also two-dimensional. So we need 4 dimensions to visualize this, which is pretty tricky for us human beings. So what we do is map the absolute value of the function, and we can use color to illustrate it. This is the absolute value here, seeing z squared, and that's why I mapped it there, just so we get a feel for. It's just the absolute value, so it doesn't have any negative values. Okay, that's good. So here's the actual base. There are a very small section of it. This is the modulus of the Riemann Zeta function. Where are we on it? Let's just swing it around a little bit. So we're not really going very far, so maybe plus minus 30 up and down the real line. So going this way is sort of the real axis. Going up and down is the imaginary axis. This is the modulus, and you can see, interestingly, that we could go on for ages about this. The zeros actually give rise to these ripples, and you can see them quite wild. They look like sinusoids. I'm not so sure if they are. Might be. But they go on forever, those little ripples. And the whole thing sort of settles down to about 1 as it goes that way. But that's not of interest to us at the minute. What counts is the critical strip, which is in cyan, and more importantly, the critical line, which is in blue. I should probably just point out this thing here, this beast is the pole. This has all been cut off. If you were to expanding, this would go up to a huge peak at infinity, and there's no point at it. So it's not defined on the pole, which is x, z equals 1, or s. There's so many different letters for representing these things. Right, so here we go, we turn it this way, and we can see there, the zeros are, well, at first glance anyway, they look to be on the line, but we certainly know that these ones are. They've been checked. And this is 0 here, so this is the IT axis, there it is. And this is going up the axis, this is going down the axis, negative, so all the non-trivial zeros occur at rho equals a half plus IT, but actually it's plus or minus IT, so it's t's plus or minus 40 plus or minus 21, so what's up here is also down there, and so on. There are also some trivial zeros at the negative even integers, which I've not ID'd, but they are trivial in the sense that we know exactly where they are, -2, -4, -6, and so on. This is a sketch of what's known about the zeros in general. If one is off the line, this one here, then it has an associate which is a reflection in the line, which is 1 minus rho, conjugate of rho, a little bar over it. And also has another associate down here, which is the conjugate of this one. It just means that the imaginary bar is negated, is negative, and it also has an associate across here. None of these have been found. Not yet. I mean, if they are, then RH is down the drain. But we have searched really quite high. Well, I personally haven't. I've done some searching. Okay, so that's where we go. We've got Riemann's trying to construct j of x. So from the zeros of his, well, it's actually his modified zeta function. I think it's called chi of x, chi of z, or s. Generally speaking, it's usually s when it's Riemann stuff, as indeed it is in the Laplace transform. Okay, so this is really the key point of this video, is a way of representing the zeros, which I took from the Laplace transform. When you transform a function, you don't really need all those wobbly bits, it's just a nuisance. So you just mark off where the zeros and the poles are. Well, here there's only one pole at 1. This is sigma. Now we're changing names because we're dealing with s equals, don't worry. This is the real bit, and this is the imaginary bit, and these are some of the zeros. I'll just put one in there to illustrate that this lot are also down here. So what this is really is a sort of schematic map where each point here represents a function across here in the real plane, which is just a separate plane drawn up. And so we can see the effect of moving sigma. So if we make sigma a little bit bigger, then we see that the rate of rise of the amplitude is increasing, and so I can't do it that way, and make it smaller. It decreases. So sigma controls controls the rate of rise of this oscillatory function, and the t element of it controls the starting frequency, basically. Once it starts, the frequency drops down, continues to drop. So that is the nature of this. And all these functions that are described, I mean, there's one for every point here, but we don't use them all. We're just using the ones that are related to the zeros. And then they're all added up, and you'll get j of x, well, pi of x as well. So there we go. This is it's a frequency modulation, so it starts high frequency and goes down in frequency. It's also amplitude modulation because it starts quite small, and then well, you can see it's going up even in this short stretch. And I think I can fiddle this out a bit further. It just carries on, you know, it just gets on and on and on. There's a sort of fractally thing going on here, but that's a job for another day. Music of the primes. It is possible to convert this into audible sound, and I have tried this and it doesn't always work. Well, let's give it a go. Let's go. I'm not sure that's working. It's a shame. I need to debug it. This may be the source of Sir Michael Berry's idea of the music of the primes. He's a mathematician, sort of got into this notion of each prime is a different note, which is reasonable. You can see that they are. It was popularised by Marcus de Sautoy in his book, the same name. Apparently Marcus de Sautoy did get permission to use it. So we look at the oscillatory functions from the first zero. So we're really looking at this function down here from the first zero. I'm not going to bother moving it. It's this one down here at 14.135. So we just look at 1. And they're all derived from a term. They're all derived. This is j of x. They're all derived from the logarithmical Li term of x to the rho, the root. They're zeros. So where is it? So yeah, this is a slightly tricky function. This Li term has a branch cut, which is often a bit annoying. It mucks about with plotting. So you can use an equivalent form, which is the exponential form. Again, I don't think this is not a regular function, a special function. That looks as though there should be an I there. This helps with plotting. But even then, it's still not clear what is controlling the oscillations and what is controlling the rate of increase of the amplitude. So here's another version that I knocked up. This piece here comes from a formula I got from Edwards, page 36. If anyone's interested, the references are in the description. There's books and videos and various bits and pieces. And the oscillatory section I just guessed at because I was working with other functions, similar functions at the time, to do with Merton's function. So, and then I just added a fiddle factor, which you can see if I shift it about. They don't match up, so I think it's 0.027. The advantage of this is you can see now clearly that the half, the amazing, mystical, magical half, really stands for square root of the x, which this controls this rising increase of the amplitude. And well, here we go. Here's the oscillatory part. it's not a pure function. It's not at all periodic, even though I believe Riemann did say in his paper that it was periodish, which is anyways not periodic in the sense that we would normally use it. Well, it might be periodic in log x, but so it's, there we are. We can see that it's the imaginary part of the 0 times the log of x, and c is just that add-on piece. So we have a lot of these functions. That's just one, and so that deals with the really nasty bit. This is what all his mathematics sort of diverting off into the contour plots and things like that, contour integration. So you get Jx is Li of x. Now this piece is derived from the pole. This piece is derived from all the zeros, the non-trivial zeros. The log 2 and this integral comes from the trivial zeros. So the whole lot add up to give you j of x, which is what he wanted. And then using Mobius inversion, you get pi of x, which is really, that's it. That's the bottom line. So that is one version of it. As mentioned before, in max, quite often you just make that infinity, but you just generate a lot of zeros. Oh, you need to make it big enough to do what you want. So the principal part of pi x is now been given a name. It's the Riemann prime counting function r of x. Yeah, there's the infinity bit. Which is a very good approximation to the prime counting function. So back to the prime counting function, which is in green, it's pi of x. There's the two happy asymptotes. And here's Riemann's first term. And it's just the first term in his series. And you can see it passes through. It's a very good fit. It's a very good estimate. And yeah, it just carries on and on to infinity and beyond. So we've now got r of x, which is the main term. So this is pi of x. There's the main term, and now we can add in the zeros. I think it does it 10 at a time or something. Yeah. So there's 10 pairs. So you have to add in the positive and the negative zeros. The complex parts will cancel out. That's leaving a real number, which is what you want, because this is in the real domain plane. So we're on 20 zeros now. You can see it's getting closer. 30 zeros, 45 zeros, 55, and so on. Actually, there's not very many zeros to get 100 zeros now. So you get a pretty good approximation of the prime counting function. Add enough zeros, you can get it as close as to what you want. It's a bit like Fourier transforms, a bit like. Right, then now prime number, right, so this is just another way of viewing it. You can do it longhand, where you sort of collect all the terms. N is 19, which is this piece up here, and N max is 19, which is because a million to the 19th root of a million is just over 2. So when you get the 20th root of a million, it would be less than 2, so the j would be 0. So you calculate all the terms. This is a table that I got from John Derbyshire's very good book on the Riemann hypothesis. References to it in the description. So you can see that the main term truly dominates. We've got 78627, and the final answer is 78498. You just get a headache. But you can see that the pluses and minuses, and they all amazingly come together to give you the answer. So there we go. Final answer for 1,000,000 is 78498, and if you ask Mathematica, just do the same thing for me please, it'll do it instantly, and you get 78498. I use a slightly larger table, out to 1,000,000,000, and they don't agree, and it's out by 2. I think that's because I didn't use enough precision on the arithmetic, or probably didn't use enough zeros in the terms of 0. It took quite a while to run, so I'm not going to bother running it again. So there we go, that's that. Now people have studied the values pi of x. A couple of guys, Kim Walsh and David Ball, used prime count, which have computed pi up to 10 to 29, which sounds big, but we'll see it's actually a very small number. I couldn't find out how long that took, but it took 5 months to calculate pi of 10 to 27, and it took 26.4 CPU core years to calculate pi to the 1028. They used a special algorithm, which I don't know what it was, and I think there was dedicated hardware. So there's the records, that's the number of primes up to there. This is just some more information. Andrew Odolitzko looked at spacings of the zeros, nearest neighbour spacing, normalized. So he looked at about 1,000,000 zeros, here we go, around 10 to the 20. So you go up the height, you go up the imaginary axis up to 10 to 20, then look at the spacing of 1,000,000 zeros, do the normalization, and then do a plot. There's also distribution can be found in random matrix theory, which really sent people down a wild alley, I think, but I'm not really sure anything was concluded. It's called a Gaussian distribution, which is rather obscure. It cannot be expressed in closed form, but can be computed numerically. I didn't bother. Well, I mean, I did, but I didn't do that bit. I just found my own fit using a simpler, the Weibel distribution. You can get the Weibel to fit this pretty well. The point being, if the spacings were random, then this would be Gaussian. It's not. It's clearly this lopsided distribution. If the zeros were distributed, they would be Gaussian. The Gaussian distribution suggests that zeros do not like to be beside each other. They don't. They sort of repel each other, in quotes. So there's a probabilistic structure to the distribution of zeros, as there is in the distribution of primes. In fact, there's many probabilistic distributions in the primes. More on that in another video. So here, all that preceded this was analytic number theory. This is probabilistic number theory, which more or less starts with Erdos-Kac theorem. That's Paul Erdos, never stayed in the same place more than once. And he worked with a hell of a lot of people. He was always collaborating with other mathematicians. Kac is Mark Kac. He's a statistician. An unusual blend, but pretty handy. So they looked at the disk. What did they do? It states, if omega n is the number of distinct prime factors of n. So omega of 6 would be 2 distinct primes. Omega of 30 would be 3. So omega of 12 would probably just be 2, because it's 2 squared times 3. So there's 2 unique primes. And they found it's a standard, or it's asymptotic to a standard normal distribution, or Gaussian. So we get some interesting things, like if you take a 10-digit number, like 1,000,000,000, on average you only need 3 distinct primes to describe it, but it's a distribution, so that's the peak average. But some of them you only need 2. Some numbers under a billion you only need 2, and obviously at primes you only need 1. So there's some variability. In some of them you need 4, maybe even 5. So we start moving on into some real numbers now, as in large number of digits. This is roughly 10,000, and that would require 10 distinct primes, again distributed. And that's this one here, so it's not particularly obvious that that's Gaussian. Maybe it's not even actually approximating Gaussian at this point. And I've got a feeling it is actually quite good even at this point. Not that you can actually get to that point. But somehow I did. I can't remember. And if you carry on 100, you're now looking at a seriously big number. 10 to the 10 to the 44, and that might be getting up close to the skews number. There we go, and at 400, you need what is that? Oh, you need 1,000 distinct primes. So there's a pattern to this. You can work out the maths. I just didn't add it there. I just called it a spreading Gaussian, where mu is a mean, which is log n, and sigma, its standard symbol, is standard deviation, which is square root of log n. That's an unusual combination, but more on that later. Right, compare primes and zeros. Primes are positive integers, nice and simple. Zeros are probably irrational. People have calculated them to 1,000 digits, and there's no digit pattern, which is often assigned. It's probably irrational. Well, it could just be monstrous rational numbers. Primes, the density of them decreases with increase in n, and so they get sparse. And now as you go further on up, but they never drop to zero. Whilst the zeros, interestingly, their density increases with increasing height up the critical line. And consecutive spacing, well, it's thought to be Poisson distribution. I've not done much work there, but I've found a couple of references. Whilst the zeros, as mentioned above, are this weird Gaussian distribution. You won't find much references to that either. So there we go. Some conclusions. Riemann succeeded in his goal to write the prime counting function down in terms of zeros of zeta. I believe it's possible to write a function. Actually, I do believe it's possible to write a function for the zeta zeros in terms of prime numbers. I remember coming across it maybe 10 years ago. I might quick look through all my various notes, can't find it. The first function builds the second function, which builds the first function, which builds, and so on. Which reminds me of an Escher image of two hands drawing each other. It is only a metaphor. They don't build each other, but they are closely woven. There is no easy formula for the zeta zeros, so constructing the prime counting function remains problematic using the explicit formula. Along the road to accomplishing his goal, he mentioned a conjecture about the location of the zeros is now the famous RH hypothesis, unsolved for around 163 years. A lot of great mathematicians have had a go at it. Perhaps some of them going slightly loopy. Perhaps his real contribution was less in the results, but in his methods, and he really did lay down some of the basics of complex analysis. So he invented zeta s, function of complex variable. He used analytic continuation. I don't think he used the name like that. He just called something else. He'd just like to take a function, sort of find extend it, make it global, make it valid globally. He studied the complex zeros of zeta. He invented this entire function. This is where the zeros come from, which is related to zeta through the gamma function. That's the product representation of this. I think it's chi. It's a strange. You don't use this symbol very much. He also invented, I think, the discrete power counting function. He used Fourier inversion and Mobius inversion. I'd like to think Fourier did that as well. I'm not sure about Mobius and Mobius inversion. He probably did. He certainly used Mellin transform. There was no reference to it. Mellin was 4 years old when he wrote this paper. I think, like many mathematicians, Mellin was kind of lucky to get his name associated with the transform when somebody else had already done it before. A bit like Pythagoras, really. Loads of mathematicians had figured out Pythagoras' theorem. Pythagoras just got the PR people to get his name on it. And he also worked with representations of functions such as pi of x by explicit formulas. Further back up there, that was whatever it is. That is an explicit formula. That's just a name for it. it sort of describes a function, but itself is got lots of difficult bits. There is compelling evidence for the truth of the Riemann hypothesis, but that is not a proof. Paul Erdos felt that we do not have the methods, and Terence Tao, one of the best mathematicians alive at the minute, and he's contributed to this area, has said that we do not have the toolbox to solve it. So is RH true or false? Well, I'm on the fence. But I do feel that we may have exhausted methods from analytic number theory, so time to find new ways. More on that in future videos. And here's finally just a timeline of various mathematicians. Riemann had a very short life, lived only 36 years. Euler was preceded a bit by Euler, who's of course a brilliant mathematician, and was provided the starting point for Riemann's research there. Laplace and Fourier. I wonder if these guys, no, they wouldn't have met because he was still a baby. Gauss was, of course, a great Gauss, Carl Friedrich Gauss. He was one of Riemann's mentors, as was Dirichlet. Stieltjes did the sort of, he defined jumps on piecewise functions to be at the jump to be the average value before and after the jump, which was pretty handy. It's just a tidy thing, I think. Mellon, as I mentioned earlier, well, he come up with the Mellon transform, which in fact is what Riemann used. And then he didn't say, he actually says he uses a Fourier transform to get back, but it really would be an inverse Mellon transform. But maybe you can use Fourier. They're all related, Fourier transform, Laplace transform, Mellon transform. Littlewood is the guy, he's an English mathematician, friend of G.H. Hardy. He proved that pi x does in fact eventually succeed, it gets outside the bounds of lie of x. And Hardy proved that an infinite number of zeros are on the line, but an infinite plus a million is still infinity. I believe 42% of the zeros are on the line. That's been proven, 42% are on the line, something like that. And Jacques Hadamard and Deval de Poussin, a couple of guys that lived way into their 90s, these guys proved the prime number theorem using work from Riemann's paper. I think the key idea is that you have to prove there's no zeros on the line, sigma equals 1. So there we go. I hope you found some of that interesting. The main thing really was this representation. And yep, thanks for watching. Bye.